As you can see from the title, this video deals with linear functions, which you might think, hey, we already know linear functions, but now we're going to look at what we call linear functions in 3-space. For the, I don't know, maybe the first half of this video, you can just kind of take notes in your binder, but in the middle of the video, we are going to be using the class notes and example sheet from section 12.4. Think about as you are standing on a hill somewhere, is the steepness of that hill, and let's say it's a pretty straight hill, is the steepness of that hill the same in every direction? Well, hopefully pretty quickly you're thinking no. I mean, if you point sideways, if you go across the hill, that's not as steep as going straight up the hill, right? Or straight down. So you can imagine that depending on what direction you're moving in, your slope is actually going to be different, okay? Even though the hill itself might be sloping at a very constant rate going up, but when you're talking about a plane like this, depending on the direction you're going, you can have a very different slope. Suppose we have a plane in 3-space, and we haven't drawn it yet, but we know that it has a z-intercept of 4. So when it touches the x-axis, it's happening right here at the point 0, 0, 4. All right? And we also know that if you were to move in the x direction, its slope would be -3. So in other words, we can think of that as delta z over delta x is -3 over 1. And if you were to move strictly in the y direction, all right, its slope would be +2. So delta z over delta y would be +2. All right, so if you walk on this plane until your x-coordinate is 3 and your y-coordinate is 5, what is your z-coordinate? I've actually given you enough information to determine what the point 3, 5 blank must be in this plane. Okay, so why don't you pause the video and see if you can figure out what the z value would have to be at the point where x is 3 and y is 5. Hopefully you haven't thought, well, this is impossible. Let's just imagine if we were, standing at the point 0, 0, 4, and we were to head in the x direction. Let's see, we need to get to the x-coordinate 3. So if we were to head in the x direction by 3 units, what would be our z value? All right, since we know that our slope in the x direction is -3, and we head 3 units, what would that z value be? All right, and once you figure that out, you'll be at the point 3, 0, and whatever z value you have, okay? And then you can move in the y direction to get over to the coordinate 5. So, what is your answer? See if this is what you got. Yes, you should have gotten 3, 5, 5. Let's walk through that just to see what's going on. So when we headed in the positive x direction by 3 units, right, because our slope was -3 over 1, we went down by 9 units in the z direction, right? So let's see, we're at 4. 4 minus 9 would put us down here at -5, okay? And now we want to head in the positive y direction by 5 units. And in doing so, we end up, right, moving up by 10 units because our slope is 2, +2 in that direction. And we end up way up here at 3, 5, 5. So there we go. So having a starting point like 0, 0, 4, and knowing the two slopes, one in the x direction, one in the y direction, you were able to find a new z value if you were given an x and a y coordinate. All right, so what we want to do now is describe all values of z that we would get if we started at 0, 0, 4, we had an x direction slope of -3, a y direction slope of 2, and we're trying to describe all the z-values we'll get for any xy pairs of values. All right, so let's retrace our steps. We're trying to figure out what our z-value is, right? And we started out at 4. Okay. From there, we figured out that we had to go down by 9. And of course, we got that because we were adding 3 times negative 3, right? So for every 3 in the positive direction, x direction we're going down by negative 3 for z. And what we need to know is what z is, right? And then we added 5 in the y direction times 2 to figure out how much of our z is going to change. And that left us at 5. Okay, so take what we just did right here and apply that to any xy pair, and you should have the equation. Pause the video, see if you can get it. All right, well, if you simply substituted in place of that 3 and that 5, the x and the y, you actually would have the correct answer, right? We're going to start at 4, and however far we go in the x direction, we're going down by 3 times that. And however far we go in the y direction, we're going to go up or down by 2 times that, right? So that should describe the equation of this plane, and here we go. Let's take a look at it. I made this plot on that website, CalcPlot3D, and you can get the link to that on the topics page in the chapter 12 topic. And you can notice I even figured out that I could actually plot the 2 points we were working with. So there's the point 0, 0, 4, all right? And then way out here, if we go 3, 5, and then up by 5, there's our point 3, 5, 5. It's not hard to do this. You just simply, once you get the plane in there, you type in your equation, then you simply add to the plot. And one thing you can add to it is an XYZ point, all right? So if you want to explore that, it's kind of fun. Okay, so we're going to change the problem up just a little bit. Instead of starting at 0, 0, 4, now we're going to start at a different point, not on the z-axis, just the point 1, 4, 4, all right? Our slope in the x direction is still negative 3. Our slope in the y direction is still 2. So if you walk on this plane until your x-coordinate is 3 and your y-coordinate is 5, what is your z-coordinate? All right, so what is the point 3, 5 blank? All right, pause the video and see if you can figure that out. Is this what you got? So if you drew it out like me, you probably said, okay, I'm going to start over here at 1, 4, 4. I'm only going to head 2 units, right, in the x direction because we're already at 1. And that would mean we're going down by 6, right, because we got 2 times negative 3. And that puts us at 3, 4, negative 2. And then going in the y direction by 1 unit, right, because we're starting at 4 and just going to 5. We're going to be going up by 2 units thanks to our slope in the y direction. And that puts us at 0 for z, right? All right, pretty cool. So now let's see if we can come up with an equation for this plane, right? Kind of doing the same thing you did last time. Only difference is now you're at 1, 4, 4. You're not on the z-axis anymore. All right, you still have your same slopes. You're still, instead of trying to get to the point 3, 5, you're just trying to get to the point, any point, x, y, and to figure out what the z value is for any xy ordered pair. Pause your video and see what you can get. All right, so let's run through what we did specifically again, right? We're trying to figure out our z value. We were starting at 4, all right? And this time, instead of heading in the x direction 3 units, we headed 2 units because we have to think we got to do 3 minus 1, right? And then that gets multiplied by our slope, negative 3. And then from there, we're going to add, let's see, let me switch colors here. We're going to add let's see, we went 1 unit in the y direction because that would be 5 minus 4. And then that got multiplied by our slope, which was 2 in that direction. All right. And that gave us our new y value of, new z value of 0. All right, so if we do this in general with x and y, we're going to still start at 4. But this time, let's replace that 3 with an x. So we'll have x minus 1, then times 3, right? And then we'll replace the 5 with a y, so y minus 4, and then times 2. And usually we'll write it this way, right? Where we'll have 4 plus 3 times x minus 1, and then plus 2 times y minus 4. And this should definitely kind of look familiar, very similar to what we did with linear functions in 2-space. You might be able to start seeing why we're calling these linear functions in 3-space, right? We just simply have 2 slopes, and those slopes each multiply either the x minus whatever the x coordinate is and y minus the y coordinate. So this is kind of point slope form, right, of the equation for our plane. Here is the graph of that plane done on our CalcPlot 3D, and I've pointed out where the 2 points are. Here's that point 144 way up here, and then here is the point 350, okay, right in that plane going there. So kind of cool. So let's write down some general things we can say about what we've learned here, okay? So definition of a linear function in 3-space is a function z equals f of xy is called linear if it has a constant slope in any direction. And the graph of a linear function in 3-space is going to be, yes, a plane, not a line. So let's write that in here. All right, now, so if a plane, or in other words, a linear function, z equals f of xy, I believe I left a parentheses set out of there. If it has a slope m in the x direction and a slope n in the y direction and passes through the point x sub 0, y sub 0, z sub 0, then its equation is, all right, let's just kind of do what we already did, okay? We're going to be describing a z value, right? So its equation is going to be z equals, and we can just start at the z value we know, right? Z sub 0 plus, and we're going to go, let's deal with the x's first. So it'll be our slope times x minus x sub 0, right? And then plus, and we then have our slope in the y direction. So n times y minus y sub 0, all right? And we can call that function, we can use z. We can also call it f of, whoops, changed my colors on me, f of x comma y, all right? Now, if we distribute some of this stuff, let's see what we'll have. We'll have z sub 0 plus mx minus m times x sub 0, whoops, m times x sub 0, plus ny minus n times y sub 0. Okay, and if we gather all this stuff kind of together here, let's see, we'll have f of x comma y. I'm going to put all the constant terms first, all right? So if we take this z sub 0 and let's see, and we have a minus m times x sub 0, that's just a constant, right? The only two variables we have are the x right here and the y right here. Three variables, and we have the z over there, okay? And then we have minus another constant, n times y sub 0, and then we're left with plus mx plus my. I'm sorry, n times y. Take that back, n times y. All right, and if we just look at all the constants and add them together, all right, that just gives us another constant. So what we end up with is a constant, let's just call it c plus mx plus ny. All right, I was running out of space on my slide, so decided to come over here to a new sheet. But so the first equation we wrote took this form, and we would call that the point slope form, right? Because we know one point in the plane, that can be any point in the plane, and we know our two slopes, right? Delta z over delta x and delta z over delta y. So the slopes in the x and y direction. And then if we distribute all this, right, get rid of all the parentheses and then gather up all the constants, we end up with this form, which is slope-intercept form, okay? And as you can see, C is the z-intercept. If you plug 0 in for x and y, you're going to be left with C for z. So that point is in the plane, and that would be the z-intercept. Maybe I should write z-intercept. Okay, z-intercept. So now let's just take a look at some examples that are on the sheet that you have. So if you want to pause and just read through this example, feel free to do that. It's kind of trying to give us how much money this airline is making depending on how many discount fares it sells and how many regular full fares that it sells. And we can see the table over here. This row over here is how many regular fares they're selling, and this column here is the number of discounted fares. And then these numbers in the middle, right, is telling us how much revenue is coming in for those ordered pairs of regular fares and discounted fares. It doesn't exactly explain, how the ordered pairs are, but they're at least, we want to think of them as either, F, D, and R, or we could think of them as D, F, and R, but R is definitely kind of what we would think of as the output variable, right? So when you get your equation, it's going to be revenue equals, all right? And you have plenty of what we would call ordered triples here, not ordered pairs. And so keep in mind, with the forms we just looked at, we just need to know what the slopes are in the two directions, right? What's the slope in the F direction? What's the slope in the D direction? We got plenty of points, right? And all we need is 1 point and our two slopes. So why don't you pause the video and give that a shot. See if this is what you got. We could have used any of these points, but of course the easiest one might just be 0, 0, 0, right? That means basically our y-intercept is 0, so it would just be 2 over 25 times d plus 6 over 25 times f. I did it out in point slope form first, but I didn't have to do that, all right, since we knew what the r-intercept was. This problem is fairly similar to the last problem in that they are giving us, they're giving us 3 points that allow us, these 3 points do allow us to get our two slopes pretty easily. So the other nice thing about these 3 points is they do allow us to sketch a graph of this plane pretty easily, right? If we draw in our 3 axes, we're going to go out 4 units in the x direction, right out to here. That's 4 units, then 3 units in the y direction, 2, 3, not doing a great job of that, and then 2 units in the z direction, 1, 2. So once we have those 3 points, right, we can sketch our triangle, and that gives us our plane. Pause the video and see if you can get an answer. Does yours look like this? Once again, because we were given the z-intercept, we could just go straight to slope-intercept form here once we have our two slopes. And you may have just looked at the graph and thought about the fact that we're going up 2 units in the z direction for every 4 we lose or something like that, rather than do out a little slope formula. Okay, so given these three tables, which of these is giving us a linear function? All right, and certainly keep in mind your output values for your z's, right, are these numbers in the middle for given x and y's. Your y's are heading across in the row, and the top of your x is going down in the column. So pause the video and see which ones you think are linear. Check and see if this is what you got. Of course, we're just looking for a constant, an average rate of change in both directions as we move across in the y direction, move down here with the x's. These tables are pretty nice because your x's and your y's, I believe, always increase by the same amount, right? Either going up by 3, down by 2, up by 1, down by 1. So you can just kind of pay attention to the z values and see if they're going up by a constant amount each time. Looks like we're doing well in the y direction here in part A, but not so good in the x direction, right? Whereas over here in part B, looks like we're going down by 5 each time in the y's, and we're going up by 3 each time for the x's. So I think we're good there. That'd be a yes. But here, we're good for the y's. We just have going up by 0 each time, but for the x's, don't think we have that constant, right? We're going up by 1, but then we're going down by 1, and then we're going up by 1. So not linear there. Okay, same kind of exercise here, just with contour plots. Keep in mind now you know your z values because those are these numbers right here, right? So use that fact to figure out if you have linear functions. Pause the video and see what you come up with. Contour graphs in some ways might be a little easier to see this, right? Because we do know that as the lines get closer and closer to each other, that our graph's getting steeper and steeper. So certainly not linear growth here for letter B. Here that looks like they're evenly spaced, and same here. However, when we look in part C, right, our z values are going down, then staying the same, and then going back up. So that's, while there might be, this might kind of indicate more like two planes, one going down and then one coming back up. Whereas here we have definitely a good decrease. And if you wanted to pay attention to certain points, you could do that. In fact, I think you need to do that here because now that we've established that this one is linear, put a little yes by that. This is a no. This is a no. All right. Now see if you can come up with the equation for this linear one right here. All right. Pause the video and do that. All right. Is this what you got? Okay. So keeping in mind we need to find two slopes, right, and then just know a point on the plane. I first looked at these 2 points here to get my slope for delta z, delta y. I can see that my z values are actually, let's see, depending on which way I'm moving. If I start here, so if I'm moving up by 2, my z values are also increasing by 2. So that's how I got 2 over 2 equals 1, okay? And then for delta z, delta x, I decided to focus on these 2 points. You can see I even did some subtraction, but let's see. If we go in the negative direction by 3 units, so negative 3, our z values are jumping up by 2 units. So that's how we're getting negative 2/3. And once I know those two, then I just got to find a point. I decided to pick on this point here, which is at 2, 0, 4, right? 4 being the z value. And there we go. So we have our initial starting z value, right? And then minus our x part plus our y part there, or plus our x part and then plus our y part there. All right. Well, hopefully you're feeling pretty good about working with these linear functions in 3 space.